Hey, everybody. As David mentioned, my name's Bill Penberthy, and we're here to kind of talk about code quality and infrastructure as code, or IAC. So I'm currently a consultant at Unify Consultant, which is headquartered here in Seattle. My specialties in systems and software architecture with an emphasis towards operations in the cloud. I've written a couple of .NET books, and I'm two chapters in 3 weeks away from completing my third, which is called Pro .NET on AWS for A-Press Publishing. I've spent oh 20 years in consulting plus an additional 10 plus in industry, and I've worked in literally every aspect of the software developer lifecycle. I like to claim, and I don't know why I like is the right word for it, but my claim to fame is that I've probably made every single possible software developer mistake out there, and I have the gray hairs to prove it. So hopefully the things that we'll go over today may help you avoid some of those problems yourself. So this is our agenda. A real quick description of infrastructure as code so that we all get on the same page as to what I mean here. We'll then talk about code quality and how infrastructure go hand in hand. We'll then go into some of the differences around code quality in an application versus code quality and infrastructure as code. And then we'll talk a little bit more about what you should do or what you should do about those differences. So what is infrastructure as code? Well, I've got Microsoft's definition up on the slide, so I'm not going to read that. So, what I'll simply say is that IAC is basically defining your infrastructure, such as your compute resources, whether it's a virtual machine or a container or a serverless function, uh, your networking configuration, your firewall rules, system rights, anything and everything that you use to provide the infrastructure on which your applications run. All of that in IAC, you define in code, infrastructure as code. The code is then checked into source code, and whenever you need an environment, you rerun that code. So this solves real world problems. Environmental drift is one. IAC offers idempotence, where where a deployment always starts the infrastructure in the same configuration every time. And since this is checked into source code and idempotent, you can then roll your environment back to a previous version. You can check out previous versions and do some work against that. These are all solving real world problems. IAC also offers real benefits beyond how it helps solve those problems. Uh, you know, One of the coolest things about the cloud is how you can spin up new instances up and down really easily whenever you need it. Is something going on, and all of a sudden you need a new testing instance of an application? Maybe to test an integration or to give a partner a sandbox to play on, something like that. Well, now it's really easy to do that because you have your infrastructure defined in code. In the old days, way back when's, typically you would have a what they call a playbook, a written set of steps that you would take to create and configure your environment. And a new environment took time. And since nobody ever really had time, it would be a big deal and it would get lot of pushback to creating a new environment. Well, in the cloud with IAC, it's now not that big of a deal. And lastly, and it kind of doesn't fit in here, but I think it's important to start bringing this up now, is that IAC should be used with a declarative definition. This means that the code that you create and manage describes what the environment is rather than how it's built. IAC is, typically you look at it as it's kind of based on a product like Pulumi or Terraform or AWS CloudFormation. And those products are kind of responsible for filling the how based upon the declarations that you provide in code. In other words, your job isn't to do it, your job is to define what it is. And we just briefly mentioned environmental drift. Let's go into this in a little bit more because in many ways, this may have been my biggest waking nightmare for the last few decades. So, as you may know, environmental drift is when there are discrepancies between environments. This happens when you have a VM or a system on which you deploy without redoing the environment. Um, very, very typical last few years, especially when deploying into Windows VMs. So I could guarantee that, like 2 years ago, when you first created those environments, they were exactly the same. Now they aren't. Test will be different because it's had things tested on it. Go figure. Whether it's an OS patch or an application update that ended up getting rolled back, at some point those environments are gonna evolve differently, which means there'll potentially be some different behaviors that are on those environments. They could be performance based. Say you bumped up production resources to 16 gig while your dev or tester at 8 gig. Um, it could also be something more significant, like different versions of installed frameworks, especially when you don't take those frameworks with you when you deploy. And that's what IAC prevents, this drift. It means that you'll be using the same environment, just like you use the same bits, hopefully, when you test a deployment and then when you push to prod. Uh, so what you're evaluating in test and what you're running in production are the same. The advent of containers has done a lot around helping manage this, and that's great. However, those of us, as I mentioned earlier, in the .NET world, and especially at enterprise companies, are still have a lot of applications running on .NET Framework 4.x, which means most likely running on a Windows VM, and more than likely that that system hasn't been updated for a long time, and you will have drift. So why IAC matters? We've kind of talked about all these points, but I wanted to reiterate them. IAC matters. Using IAC makes your environments more predictable, and that has a lot of value in and of itself. So here's an example of IAC using Pulumi and C# to define what is it? An Ubuntu instance on a T3 micro instance type. So what this is we've defined the operating system and some other ancillary kind of software that we want installed on it, and we've determined with the instance type what size of processor and memory availability and network connections do we want to have available. So we're basing this on a well-known machine image here, the Ubuntu slash images. You can see that in the first part of the get Amy filter args. But what this means is if you choose the proper uh, AMI here or Amazon machine image for this one, that you can get Ubuntu with .NET Core already installed on it, which means that before you use this EC2 instance, before you do anything, it's already defined and it's ready for use. So by using this, all of a sudden now, any work that you have to do after starting your your environment is already done for you. And so that eliminates a lot of those problems that we used to have with the playbooks around having to manually manage some of those workflows. So here's a different approach where the instance is defined in JSON. This is an example for the template definition for creating an AWS EC2 instance. So you can also create these definitions in YAML, but personally, YAML drives me crazy, so I didn't include those. Um, Filling out these values and running it in AWS CloudFormation will create the instance. Now, if you look at these, you'll see what you're doing is you're describing what the configuration is going to be, what the um, hardware item that you're going to be deploying is. You're not telling the system how to do it. You're instead just defining this is what I need to run my infrastructure. Now, an interesting thing about this is that the code that we looked at on the last slide, typically what you'll see with that or with like the AWS's Cloud Developer Kit is that you're able to create code in the language that you're familiar with, and what it ends up doing is it outputs these definitions. So you're able to use those kinds of C# constructs that you're used to, but you're going to end up building these kinds of JSON uh, templates that the cloud providers themselves are going to understand how to work with. So that's a huge value of that. So think about that. We'll talk about this a little bit more when we get into it, but think about as your code quality and approaching how you're going to be building this infrastructure, how they are starting to interrelate. And that's kind of what we'll go over now with you know, IAC matters. And the rest of this conference kind of talked about code quality and how that matters. So let's kind of mash them together. So first of all, let's go over what code quality looks like because these are the points that I'm going to kind of come back to as I go deeper into IAC and how that works is, we won't worry about a definition or anything like that. Let's just talk about the characteristics of quality code. And when we touch on these, think about them in the context of your infrastructure and not just your application. Does what it should. Huh, okay. That's something I really want out of my infrastructure. I don't know about you, but I really want it to just do what it should. And next is easy to understand. That gets a little bit more complex when you're starting to think about about infrastructure as code, because let's be real, not everybody is used to IAC, and there's a lot of developers, especially in the older generation .NET world, that don't have much experience in systems and infrastructure at all. So everything we could do to make the next guy that comes along be able to perform something meaningful with the infrastructure code becomes important, and that's where quality comes out. So the code should be well documented. This seems to go hand in hand with easy to understand, but consider what that means for IAC. First of all, the the rate of change in code in IAC tends to be much lower than it is in an active application. It's pretty unusual that you'd be changing your environment every release, for example. You could. I mean, definitely you could, but generally you'd be running the same environmental code for a longer period than the applicable application code. I mean, you'll still include it in every release. You just won't have had put any change sets against it. So obviously, once an application goes into maintenance mode, it's completely possible that the only changes that you'll do is maybe like a quarterly OS security update, but that's generally not the case. But because it's updated the least frequent amount out of all of those parts of your system, uh, documentation becomes even more important because I don't know about you, but if I go back and look at code that I wrote 3 months ago, I still have to spend that minute or two scratching my head going, what was I thinking? Um, and the last point here is that quality IAC code can be tested. This is huge because a primary differentiator between IAC authored by a systems guy and an IAC authored by a developer. We'll go into this in more detail later, but think about your infrastructure in a way that means you have common coding concepts like separation of concerns and code reuse, and all of the other coding techniques that you use to ensure that you're writing quality code in your application, that you apply those to your infrastructure as well. So, what does quality code affect? Well, first thing is reliability. The probability that a system will run without failure over a specified period of operation. Ah, okay, that sounds pretty good. I think we'd want that as our infrastructure as well. Maintainability. How easily the software can be maintained, size, consistency, structure, and complexity of the code base are all part of that. Useful documentation plays into that. Testability uh, measures how well the software supports testing efforts, how well you can control, observe, isolate, and automate testing. Portability measures, how usable the same software is in different environments. And reusability, whether existing assets such as code can be used again. So when we go into the different solution points, these are how we're going to compare them back to, or these 5 points right here. So we've talked about IAC, we've talked about code quality and the importance of quality code on successful IAC. Let's go point out some more of the differences between normal code or code in an application and code used in infrastructure as code, and how it could affect things differently as you think about it in code quality. So there's four major points that we're going to talk about. The first is the footprint of effect. The second are the failure vectors, or the different ways in which a failure can occur. The third is the complexity of testing. And the fourth is the unusualness of the problem set. I put that in quotes because I wasn't sure it's a real word, but I really like it, so I'm keeping it anyway. Um, the footprint of effect. How much stuff can be impacted by poor quality code? The first point is that an environmental failure or misconfiguration or simply poor quality can cause an outage in the application. And that may be the only cause of the outage. But of course, since it's the application, everyone will blame the application first, unless, of course, you're one of the app developers, in which case it's the environment, but nobody will believe you. But there's a lot of problems that a poorly configured environment can cause. Think about it. If the database driver that you may need isn't installed, or a route isn't open in the firewall, or access rights aren't given correctly, the application won't work. But it will take some research to figure out why. Is the code wrong, or is it something somewhere else that's making the problems? And even beyond the application, a lot of things that a modern system relies on, such as tracing or alerting, logging, all could be broken because something went wrong with the environment. My favorite was once where the environment was so broken that the alerts we used to tell us if something was wrong, well, they wouldn't fire. It was so broken that our systems couldn't report that it was broken. And so we didn't expect it to be broken, and we just kind of skipped that whole part of the troubleshooting process. And all of these shows how these dependencies trickle down. You know, if logging doesn't work, for example, you may not notice it until you have to go look for a specific problem. So now you have two problems. One, the app is hiccuping and you're not logging it. And why? Because your infrastructure code is of low quality. So let's visualize what I was just talking about. The blue box is your application. Everything else around it is what you manage and impact when using an IAC to manage your infrastructure. Thus, an IAC deployment can affect everything inside and including the white box, which is your network boundary. So not only is the problem or potential problem the application, it's everything that the application communicates with. So all of these different points become your failure vectors, or the most common direction in which errors can occur. Poorly designed IAC could affect networking and connectivity. Imagine something like a firewall rule misconfigured or a routing table entry missing, or anything like that that talks about network and communications within the network. Monitoring, as we mentioned above, but that's another direction of failure. If you have to ensure that your code quality extends to that code that's managing the monitoring of configuration and setup. And lastly, the actual processing of the infrastructure creation. Much of this is out of your hands, but there are definitely some quality decisions that you can control that have a significant impact on how everything is put together and processed by your IAC tool of choice. And here's another visualization that kind of shows the extent of IAC slightly differently, because it can also impact your ability to connect with other systems or even managing the rights that you assign your own resources. And because of the failure vectors, managing the testing is very difficult. Think back to when we went over the characteristics of quality code and how one of those main characteristics was testability. Well, the complexity of this testing effort makes it even more critical that the testability of the code is maximized. Sure, more than likely the release schedule for your infrastructure changes will be different than your application changes, but you need to make sure that you have enough time to manage these testing needs. And we'll go into these in a little bit more detail in a bit. And lastly is the unusualness of the code in IAC. Well, why is it unusual? Well, first of all, it describes infrastructure. Many developers do not have the most complete grasp on the intricacies of the entire cloud system. A VP, for example, or virtual private cloud, is generally pretty well understood. But knowing that you need to add an internet gateway to that VPC before you can access the internet requires a deeper understanding of the peculiarities of whichever cloud provider you're using than most developers really wish to have. Another unusual, I'm sorry, I went too fast. There we go. Another unusual difference is that the IAC describes what the output is rather than how to build it. This is a strength of IAC because that makes the outcome more predictable. But it's the opposite of what the normal developer behavior is developers tend to focus on how it gets done because they're generally the ones that are responsible for doing that. And lastly is that it should be treated at the same level as an application. What do I mean by that? Well, many times you kind of see structure considered to be part of an application, um, generally because of how tightly bound they are. But just like those visualizations that we went over a little bit ago, um, it puts the infrastructure in an inferior position. Um, and what that means is that people then start looking at the infrastructure as being subordinate to the application when really you should be thinking of them as being at the same level or partners in it rather than one of them owning the other one. Even though, to be honest, the sole purpose of the infrastructure is to run the application, we need to break that mental model about the infrastructure being subordinate to the application. And arguments against it being different. So I've heard the argument that the infrastructure should be considered to be similar to a framework or an SDK. They're similar at that there will be changes and updates to the framework, but there are very likely to be a lot fewer of those changes. And also, any quality issues in the framework could result in incorrect behavior in the application, just like it would when looking at the infrastructure. So that argument says there's no real difference between being a framework module and being IAC. And there are definitely some similarities. But we talked about those vectors for failure earlier, and that's where I think IAC needs to be treated differently than a framework or other application inclusive items. Once again, if you're going to look at it as subordinate, then it would make sense to kind of consider them even more. But the fact that the infrastructure can have many other things that could cause problems other than the application makes me think that it should be separately. Another one that talks about complexity and how there are other systems that are complex as well. You know, this too is true, but I think it kind of misses the point. The examples that were given speak specifically about systems. So a group of applications working together to fulfill a set of requirements, while perhaps being complicated, is still really application bound. Whether an application is one of them with a million lines of codes or 100 separate applications with 10,000 lines of code, the failure vectors are different between the applications and between the infrastructure. And lastly, code is code is code, so that in regards there should be no differences between IAC and application code. And in many ways, I actually feel that this is the most compelling of these arguments. However, there are some things that you'll need to do differently when you look at IAC as opposed to regular code. And lastly, there are some additional considerations that are mostly burdensome on the infrastructure team. The first of these are uh, pre-established company standards around generally IT governance or security or things like that. The standards talk about when and how and why IT infrastructure changes can happen and how that change needs to happen, who has to approve it, and so on. You can't just throw those standards out when you go to IAC or exempt your infrastructure from them. Imagine what would happen if say some big audit came through and you have systems that aren't following your company's published IT standard. Well, you'd probably fail that audit, and that could be a very expensive proposition. The next consideration is industry compliance. There are additional controls put on the infrastructure if you're in a PCI compliant environment or GDPR or any of the other kind of industry led standards and rules. Both of these are considerations that put additional burden on using IAC, and it helps, I think, explain why code quality needs to be important and how those decisions need to be made. So, what do you have to do to ensure quality in IAC? Well, we talked a little bit about audits and governance, but these are definitely factors that you have to take into account when building infrastructure. While not a quality code construct in and of itself, audits and governance, uh, they provide the structure and methodologies that are going to be enforced through infrastructure as code. These structures need to be managed in a more rigid way than just assuming they're one of the set of requirements um, that you're going to use to evaluate your testing success. Instead, reviews and audits should really be set up before the infrastructure work can be performed, such as deployed to a new environment. These reviews are all around compliance and whether or not the infrastructure meets the various needs and requirements that they've got. And that's the key to this: is whenever the infrastructure is changed, no matter how small of a change, you must confirm that you're still in compliance. And that's more than just a QA test. You need to be much more formal about it. So a governance audit. These help support the reliability of your infrastructure. And next is a golden construct, because once you have governance, this is the best way to ensure compliance and audit management. This is your definition of each part of the infrastructure. If you're using virtual machines, then you should have the golden construct for VMs that you want to use. You should keep these numbered to the smallest possible. For example, Don't have a golden construct for Ubuntu and a different construct for Debian unless you really, really, really have to support both operating systems. Instead, standardize whenever possible and use variables to manage those real differences. If you think back to the IAC code that I showed earlier, this one, think about what makes sense to support different variable driven settings. Um, for example, I think that we'd want to easily configure the AMI value because that could be different from one another. And in many ways, that could easily impact the application. And we certainly know that we want to do that with managing the instance type or where we define the size of the machine that's to be started. I mean, that's a logical place to get started because it's easy to see what you may want to use a different size of hard drive and memory based upon the workload that you're looking to work with. So your golden construct is really a series of constructs. Each one of your infrastructure components needs a golden construct. Thus, your infrastructure is really a bunch of gold kind of stitched together as a unified whole, kind of like how a chain necklace is made up of golden links put together. Since your golden construct is literally defined as the definition of that construct that could be used anywhere, then the reusability expectations for code quality are satisfied. These golden constructs also obviously help drive reliability as well. So, automated testing, as I hinted about earlier, is massively important and massively complicated. You can obviously use automated application testing to get some assurance, but when you have to ensure that you have a way to manage the testing of all the rest of the different aspects, some of this you could do through post deployment integration testing. Um, you know, I saw one approach where they ran an automated UI based testing after every deployment as a smoke test, and and that test series was a set of test paths that were really carefully calculated to hit every service, database, and external data feed that the system relies on, thus making sure that any potential infrastructure or coding changes didn't impact the ability of the application to function. Generally added 15 to 20 minutes to every release. So at a release cycle of every 2 weeks, the cadence and the extra time was pretty minimal. The other area of concerns, the alarms, performance, observability, those kinds of things. There's no real standard way to do this because it really depends heavily on how you manage your operations. But there are some ways that I've seen put this together quite successfully. I've seen, for example, reports set up in Splunk or whatever log monitoring platform that you may use that evaluates all the incoming data post release and analyzes it against previous releases and then calls out any differences. Some of these differences are expected because of code changes, new features, and things like that. But others come as a real surprise, and those are the ones that you look for. Imagine back to the example I gave earlier, where our system was so broken that we couldn't even tell that it was broken. Um, this would have helped us figure that out much sooner. These don't replace your traditional anomaly scanning, but instead are special dashboards that look for expected input that's missing. And lastly is the code quality tools. We've just seen several talks about those. These tools use various approaches to scan your source code and look for code smells or areas where things like maintainability based on coding standards such as test methods. What is it? Test method names that need to follow a standard convention, or naming conventions that are followed for constants, methods, and property. Those kinds of rules. Boy, I'm drawing some blanks on the rest of them now. Uh, my favorite line about this is Sonar Cube's got the coding standards rules promote civility. I really enjoy that. And if you saw Abhishek's talk earlier, you'll realize that you've seen this capability in more detail. I think you went over Sonar and Terraform, and we just saw some things with the editor config. But these are all powerful tools to help you statically analyze your code for potential issues around quality. Typically, you most commonly see these being configured to run during a build, say when your unit tests are ran. But I've also seen it set up as a gating event where you can not complete your code check-in and because of concerns raised by the tool. Generally, these tools are best suited for application code, but they are getting smarter and smarter around code smells and IAC code. So this will be interesting to watch over the next few years as it fully matures. I expect that, you know, probably in the next year or two, things, open source tools like AWS's Cloud Developer Kit will be pretty powerful about helping us understand and diagnose the same amount of problems that you're seeing with things like SonarQube or check marks. But unfortunately, we're not able to fulfill every aspect of code quality when you consider IAC. Um, One of the examples that I mentioned earlier was that portability is a good goal of code quality. Unfortunately, at this time, that's not possible. Even when using a third-party tool such as Pulumi, they're unable to build out an abstract model that can run across multiple providers easily and safely. However, they're getting better and better at this every year. So there's still the opportunity that at some point you'll be able to write infrastructure code that can be deployed against many different targets. Fortunately, I don't think we're there yet. Now, in summary, there are four different approaches that help assure quality code when working with IAC. Um, Audits and governance. You're most likely going to have to perform these anyway. So rather than looking at them as a chore, take advantage of the structures that they offer and use them to support quality code. The next is the golden construct, that one representation of your infrastructure. You should only make updates to your golden construct when you're, I don't know, 105% confident that they can do the job, because this is your definition of your infrastructure. Remember, I call it a golden construct, but think of it as a combination of little gold things all kind of combined together, with each infrastructure component adding to the strength of the overall construct. Next is automated testing and evaluation. This includes regular application testing as well as integration testing that stresses, every part of the system. This should help you determine things like system rights or installed software problems. As part of this, you also need to come up with ways to ensure that other areas relying on your system is validated, like alerts, logging, all those other things that you rely on to be able to ensure that your operational systems are up and working correctly. Well, you need to make sure that those still work after an evaluation or after a change as well. And lastly, take advantage of code quality tools. They're getting better and better at accessing IAC code.